let's go.
Great. Hi everyone. So thanks for coming. We're very happy to have Jamie Shotton here, who is Chief Scientist at Wayve. I've known about Jamie's work for many years. My PhD was in computer vision when Jamie was at Microsoft Research, and he was head of the mixed reality and AI labs there. And so he did a lot of the early work on HoloLens and Microsoft Connect. And then more recently, he's moved to Wayve, which, as you might know, is a very successful UK-based driverless car startup. Startup? Still startup? Company?
We call ourselves that, but maybe we're a little bit bigger now.
Somewhere between startup and the next big thing. Well, you are the next big thing, probably. So, yeah, thanks very much for coming. I'm very excited because I actually got to be in a driverless car, one of the Wayve driverless cars in May this year, ICRA. And I was surprised at how smooth it was because the kind of principle behind Wayve is to do end-to-end driving from imitation learning methods, and that's very appealing to me because that's what I work on myself in manipulation. But to see it happening in a car when there's pedestrians and other cars around was very, very exciting. And just very surprisingly smooth. And apparently it's got even better since May. So I'm very happy to have Jamie here, and thank you, Jamie, for coming, and over to you.
Thank you. Well, thanks for the kind introduction and the invitation to speak to you today. I'm super excited to be here. Good afternoon, everyone. I'm going to be talking about some of who Wayve is, what we do, the approach we're taking, and some of the research that's going on in the company. So first off, driving, right? We all love driving. The blue skies, the panoramic vistas, the open road, the thrill of the acceleration as you floor it, right? Wonderful. Well, the reality is a lot more like this. And for the average driver in the US, for example, they will spend 50 hours a year stuck in traffic jams. In the UK, it's more like around 30 because we drive a bit less. But that's a lot of time, right? That's a day or two of their 24-hour blocks of your life gone. Wouldn't it be wonderful if you could use that time constructively, creatively, or to relax, or to engage with your family and friends? More seriously, of course, there is a terrible toll that our ability to move ourselves around the streets takes on society, and millions of people killed and injured across the world every year. And if you drill into the statistics here, right, the vast majority of those are down to human error through speeding, aggressive or reckless driving, distracted driving, chemical impairment, or being tired. We should be able to fix this. And beyond those societal goods, there's also a huge economic potential here, right? We spend a lot of time and a lot of money transporting people and goods around cities and around the world, and the market, at the end of the decade for autonomous driving is estimated to be, in the trillions of dollars. People have been looking at this problem for quite a while now, in various shapes and sizes. The earliest thing I could find was this, which was a radio-controlled automobile from the 1920s, which had a sort of follow car with a radio transmitter and could do some form, I don't know any of the details, but some form of steering and actuation of the vehicle in front. I found something a little bit more robotic-like, looking like modern robotics, sort of from the 60s here with the Stanford cart. And that was, again, I think a remote-controlled thing. But here they were passing video to the controller who was driving this manually. And this was sort of designed for moon landings and things like that. To my knowledge, this is one of the earliest pieces of work on actual autonomous driving from the 80s now. And this was actually remarkably ahead of its time. It took some very low resolution camera inputs, passed it through an absolutely tiny neural network with 29 hidden units. And that would then control the steering It wouldn't do the speed and the longitudinal acceleration, deceleration, but it would control the steering. And yeah, this was really quite amazingly ahead of its time. But I think it was probably the DARPA challenges in the 2000s, mid-2000s, first the grand challenge in the desert, and then the urban challenge in a more city-like environment, that really catalyzed the public's imagination and showed that actually maybe this is possible, right? Nobody had done it before, being able to drive these kind of vehicles across a desert successfully, or navigate city streets successfully. And this really, I think, catalyzed a huge amount of excitement and investment in the space from around here onwards. And this has really made it one of the space races of our generation. It's really hard, really high potential impact. And there's lots of competing people going after this prize. And that in turn has led to all of these kind of startups and names, some of which you'll recognize, some of which you may not. But there's a lot of people looking at this space, and they have been for now quite a while, 20 years or so, in quite serious with quite serious investments, with of the order of a few $100 billion of investment flowing into this space. But they're not here yet, and they haven't been here yet for a while, and we keep hearing that they will be here. And it's interesting to think about why this might be. I think part of this is very much overhype, right? There's these have been oversold. Oh, they're just around the corner, and part of that's genuine, part of that's perhaps less genuine. But they just haven't. It's been harder than people anticipated initially, and there are various reasons for that. The one I want to focus on here is the technical reason and the approach that's been taken to do this, which I'm going to call a sort of traditional approach, or AV 1.0. And it looks a bit like this. So, this is your sort of architecture diagram, if you will, of the system. You've got sensors on the left, and typically people would throw as many sensors of as many different types as they could at this problem, because they thought, oh, well, it's all going to help and it's all going to add value. Then they're going to throw that into a perception stack, and that started with very hand-coded rules, and then in the 2010s started to become more deep learning focused. But it would do things like lane detection, or detect traffic lights or pedestrians, or bounding boxes around cars, etc. And simultaneously, there'd be a localization module. So they would go and scan these environments. We now had great computer vision technology that would reconstruct environments at large scale. Andy's been a key part in that space, and able to build these giant maps and then localize against those maps as you drive around. And that tells you, oh, I'm in this lane, and that's really useful information you can have to drive. And once you've got all of that perception stuff done, then you go into the planning module, and that sort of predicts what other actors are going to do and where you should go, and decides what you should do and act and do next. And then that goes into a control system, which actually actuates the brake and accelerator and the steering. And just to sort of give you examples of the kinds of maps that are being used. So they'll go around with a LiDAR scanner, scan these environments, the whole cities in great detail, and then they will semi-automatically label them with lane markings, positions of street signs, etc., etc. So awesome if you've got it, right? This is great, and I would love to have this in some sense, but we'll come on to the problems in a moment. And then, just to illustrate the kinds of perception outputs they'll have, they'll predict bounding boxes of all the vehicles, and they'll predict those blue trajectories of where vehicles are going to go, and then the green trajectory is the plan for the ego vehicle. But despite some notable successes and deployments, most particularly Waymo and Cruise in the US, in San Francisco, and a few other cities, they've proven very slow to deploy and scale up, and expensive to do that. And in fact, over the last couple of weeks, we've seen Cruise actually massively throttle back its operations. I think they've actually completely paused them as of yesterday, based on various things that happened there that really shouldn't have, and their rush to get something to full driverless. But the sort of, to come to the specifics, HD maps are great if you've got them, but they're very brittle, right? If something changes, if there's street layouts change, if there's roadworks, if the season changes, perhaps even, that can break these things, and you can maintain them, and people do, but they're very expensive, and they actually become quite a dominant cost in the operations of these companies using HD maps. LiDAR sensors are great. They fire off rays of infrared light and tell you the time it takes to get back, and so you can compute the distance. I love depth cameras. I've used them in my past life, but equally they're very expensive. They're very hard to integrate, and that really limits how well you can integrate these into actual deployments and consumer vehicles, for example. And last but certainly not least is sort of the use of hand-designed rules, whereby you'd say, oh, if there's a traffic light, then you're going to stop, right? Things like that. People would literally manually code that with a big nested set of if statements, that kind of thing. And lo and behold, that's quite brittle. And again, you take it from one city to the next. The driving culture changes. Take it from one country to the next, etc. Now, so that's what's been happening in AV for the last 20 years or so. Simultaneously, let's look at what's been happening in AI, and none of you nothing kind of escapes your attention. That there's been just enormous progress in non-embodied AI. So things like ImageNet being solved, things like ChatGPT and DALL-E 3, things like Mu0 and AlphaStar, and things like AlphaFold, right? All of these major breakthroughs over the last 10 years, and all through various forms of large-scale deep learning and increasingly large-scale deep learning. What's underpinning this? Well, it's a number of factors. So it's things like large training data sets and benchmarks that have allowed us to go after non-toy problems, allowed us to compete in the academic community and even internally in companies, and very fast feedback, very fast signal about how well you're doing. Things like in the world of reinforcement learning, games and simulations, and the ability to do self-play, and again, rapid iteration, fast feedback cycles. Self-supervised learning has really unlocked an enormous potential, the enormous potential of internet scale quantities of data that previously you'd have to manually label, and that just doesn't scale to the internet scale. So, being able to do self-supervised learning really unlocks enormous potential. Foundation models, where you can learn some big general purpose model. A lot of them are language models today, but there will be language and vision and action models in the future. And then to take those big models and fine-tune them or prompt them for a particular application, again, allows you to learn from a very large, diverse set of data. Compute, GPUs, availability of those, availability of GPU clusters and massive hyperscale clusters in the cloud. And simultaneously, the architectures like transformers that allow you to utilize those effectively for parallelized training. And things like scaling curves and scaling laws, where you can predict before you spend your $1 million on your compute job, you can predict that it's actually going to do something good. And then, time and time again, we're seeing that these scaling laws hold, and that you can, predict in advance how these things are going to go. Increasingly, multimodality, as I was suggesting a moment ago, right, bringing not just language or just vision or just robotics, but bringing those all together and seeing the effects compound, and the unique capabilities of each modality, playing off each other and helping accelerate the whole. And I think last but not least on my list here is this in terms of RLHF, alignment with human feedback, and that again allows you to take a lot of in the wild unstructured data and then fine-tune it for a particular application with a much more limited and scoped set of data. And this is sort of taking it all together. And I think there are other things like increasingly large uses of open source and things like archive to rapidly disseminate publications and advances. But that's where I've landed for this slide. And so coming back to these advances, I'm very firmly of the opinion that over the next few years we're going to see the same rate and pace of progress in the space of embodied AI. And for us at Wayve, of course, that's all about autonomous vehicles, but we're going to see the same thing in other robotics disciplines as well. So, looking at the busy streets of London that we drive on, here, it was very clear to us that we needed to take a different approach to this AV 1.0 world and technical approach that had been happening, and to go after solving autonomous driving as really an embodied AI problem. So what does that look like? Well, this is what it looks like, right? Super simple. Sensors, again, on the left and control on the right, but in the middle, instead of that complicated mess of lots of different components, lots of them hand-designed interfaces, you'd have just one big neural network. And simultaneously, we wanted to make this something a lot like how we drive as humans. You can just get into a car in any city, and yeah, you might need some sat-nav directions, but you know how to drive. You don't need to have pre-scanned that city and built a high-definition map. And finally, we wanted to have a lightweight sensor stack, right? We do it with 2 eyes. Some people do it with 1 eye. And sure, we don't want to go to the absolute minimum here, but we don't need to throw everything in the kitchen sink at this problem either. And so, AV 2.0 is what comes out, right? It's because of the mapping, it's very easy to deploy in new cities and countries and cultures. It's much easier to integrate into vehicles, and you get policies that align very much with human driving rather than very clunky robotic-like policies with more traditional approaches. And so just to give you a little picture of what this looks like, this is obviously very sped up, but this is us driving around for about 30 minutes around central London with 0 interventions from the driver, cameras only, sat-nav, low-definition sat-nav map just telling us which direction to go, basically, and learned fully end-to-end. And you'll see all sorts of complex, busy traffic, giving way to pedestrians, giving way at T-junctions, negotiating fairly narrow streets, waiting for a bus to pass there. And again, nothing here has been programmed. Like if it stops at a traffic light, at a red traffic light, it has learned that through example. We haven't told it anything explicit about traffic lights other than the data. And this keeps going on. And one thing we really love about London is it's actually a really challenging playground compared to a lot of the places in the US. So maybe that AV 1.0 stack works reasonably okay in big US cities where the streets are much more structured. But is it going to work in London? No way. And so we found it a really great proving ground to test this out. And just, now back at normal real-time speed, just a few examples. Top left is some negotiation and some complex intersections. The top right there, you see we've pulled into the side and let this van past. Bottom left, we've got, there's a bit of clutter on the road, a newspaper. We've just learned to ignore that. Whereas on the bottom right, there's a bin that's been tipped over, and we've learned to, safely edge around that. And, these are some complex cases that in a more traditional approach, you'd have had to manually code some special case for this. And the problem there is there's a long tail of things that could go wrong, and you just have to gradually work down that long tail and program each one. Whereas for us, we just see this emerging. The more data we train this off, the better it performs, and you get these emergent behaviors. We've also tested its generalization. So this was from last year, but we took a model that had been trained in London only, and then deployed it in Cambridge, Coventry, Liverpool, Leeds, and Manchester, and lo and behold, it drove pretty much as well as it does in London, without any additional training data. Again, reinforcing the this approach, the relaxation of the need for maps and things like that. And sort of just again to sort of jam home the message of generalization, we've outfitted now 2 vehicle types, a car and a van, with basically the same sensors, same compute, and even the same model. And so here you're seeing exactly the same neural network, same weights running on 2 cars. The top car's the top one's the car, the bottom one's the van, and the van happens to be following the car in this example. And it's just driving around. And has learned how to generalize across different vehicle types. And we saw that data from the car improved the van's driving and vice versa. We've had the privilege of having a couple of VIPs in the recent past. This video is from Bill Gates when he came to visit, there's a full video on YouTube. But we had some pretty complex maneuvers and negotiation we had to do in London, sort of holding back to overtake a bike when it was safe to do so. And then, one of my favorites is this one where it's just like, just crazy unscripted stuff that you couldn't hope for. But, we just, handled it with ease there. More recently, we had the Secretary of State for Transport, who we took from the Department of Transport to the House of Parliament last week to introduce the new autonomous vehicle bill in Parliament. Again, fantastic ride through some really challenging streets, very central London, working really, really well. So I'm going to now, that's sort of the introduction section. I'm going to now drill into 3 research highlights and some of the work that we're doing at Wayve to see, okay, we've got a system that works. How do we accelerate it? How do we do things? How do we push the envelope and what we can do? And the first is all about language, how we can use language to improve driving. And this really touches on all of these themes that we talked about earlier, especially multimodality. So if you just go to ChatGPT and ask it questions about driving, it already has a huge amount of knowledge about the driving task. And I won't read through this all in detail, but you can have a dialogue with it. You can say, here's a scenario, what should you do at a high level? And then you can sort of go query it again. Well, how would it change if, here it was, you're driving next to a school, and it will give you a pretty plausible answer. And again, well, does it still hold true if that's midnight? And again, the answer will change and be fairly nuanced here. So, these language models do encode a huge amount of common sense, as it were, in terms of reasoning capability. And wouldn't it be great to sort of be able to leverage that somehow for driving? So with that sort of thought experiment, we then sort of thought about, okay, well, what are the different ways you could use this? The 3 that sort of have come to mind so far are explainability. This big end-to-end neural network, how do you convince people that it is safe, that it knows what it's seeing, that it's able to do what you think it's able to do? And then multimodal training and reasoning for driving, which I'll talk about a bit later. So let's dive into explainability. And so here, where we've got to so far is something called lingo, and I'll introduce that in a moment. But essentially, you take a snippet of driving video, and then you can ask questions about it in a chat interface, and you can ask it things about what it sees and what would happen if something changed in the scene, what it's planning to do, what are the rules of the road, what it's paying attention to, etc. So this is Lingo 1, and essentially it looks a little bit like this. You can read more on our blog, but essentially there's a clip encoder and then a video encoder. Pass that into a large language model that we fine tune, and turn that into a chat loop. So sort of super simple architecture. It's mainly about the data and how you train it. For this, the nice thing is you can throw kind of as much data as you can find at it of different sources, some manually labeled, some simulated, some automatically labeled, some data from our safety operators who are driving around behind the wheel, sitting behind the wheel most of the time, but looking after our vehicles. And you can just bring that all in there, and then some RLHF on top of that. And then you get sort of results that look a bit like this. So this is, first of all, in a sort of commentating mode. So, top left, I'm staying stopped behind a bus. I'm accelerating from a stopped position. I'm turning right to continue on my intended route. I'm overtaking the bus that's coming to a stop, etc., etc. You know, here's another one. I'm maintaining my speed because the road is clear. I'm slowing down due to a jaywalker. I'm slowing down in preparation for the upcoming left turn, etc. Top right, slowing down because I don't have the right of way. I'm slowing to complete stop since I don't have the right of way, and that one stays stopped for quite a while, so I'll start the bottom right one while we're waiting for that one. Slowing down at the junction due to an oncoming vehicle. I'm slowing to a stop because I don't have the right of way. I'm proceeding slowly due to the narrow path. We'll start moving in a moment, and then the top one's now turning right because the lane is clear. So, you know, this gives you a sort of running commentary of what's going on, and really, you know, interesting there. But where we went next with this was this question-answer system, and you know, so this is a video here. Why are you stopped? I'm stopped because the traffic light is red. What are the top 3 hazards you're paying attention to? Top 3 hazards are traffic light, cyclist, and the pedestrians crossing the road. Why? Because they can impact my safety and others of the road. When can you go? And go when the traffic light turns green, you know, etc. So this kind of interesting dialogue, and it's certainly not perfect yet, and needs more data and more training, but already gets some really interesting things coming up. And you can ask it, you know, other things like, what's the weather like? It's rainy, and do you drive differently in the rain? So, you know, tying not just the visual perception, but also how that perception leads to action and should, you know, should affect you, and all these counterfactuals. And so, you know, how come you should drive more cautiously in the rainy conditions? Well, the road might be slippery and visibility might be reduced. When can you go? I can go when the black sedan in front of me starts moving. When will it stop raining? Can't predict that. Is it true that it always rains in London? Drum roll. No. It is known for its rainy weather. So again, you know, this starts to build a picture of what you can do with these end-to-end models and still get an understanding of what's under the hood and how you can interpret their decision making. And I'd say it's very early days yet with this, but it's a very exciting direction. But looking ahead, I think there's a couple of things that are very exciting. One in particular is multimodal training. So right today, most of our training data is based on actual videos that we capture from our cars as we drive around. But you know, what if we could also throw language into the training? So for example, you could take the highway code as it's written in law and just feed that in as an input. And then when you go to another country, well, you can feed in their laws and it would drive differently according to the different laws. Or, you know, you could describe this scene. I mean, this is an interesting, complex scene, but I could describe in a paragraph what is important and what you should be paying attention to, and you know, what the causal factors of your decision making should be. So, right, you know, you can't move until the pedestrian crossing is clear. There's other pedestrians past the crossing. When you get to the crossing, past the crossing, there's a T-junction, so you have to give way to traffic, to cross traffic. When that's clear, you can go, but you're not allowed to stop in that yellow crosshatch box. Oh, and by the way, the traffic speed limit has dropped to 20 miles an hour, so you're going to have to slow your speed. So again, just a very 4 or 5 sentences, you could describe this scene in a way that might take thousands of videos to get it to learn. And I think there's a real opportunity for very, very efficient learning using this kind of multimodal training. And of course, another thing that is worth exploring, and we and others are also looking at, is actually using the language model in closed loop for driving, where, you know, maybe the simple cases are handled with a, you know, simple feed-forward neural network, but then you have some kind of reasoning passed out to a large language model for more complex maneuvers. So lots of exciting stuff there, but I think in the interest of time, I'll move on to the next topic, which we're calling neural replay. And this is really all about how do you measure stuff, right? One of the biggest challenges with autonomous driving is measuring, because if you go out on the road, everything changes from one run to the next. The weather changes, the driving changes, the dynamic traffic changes. And so it's very, very hard to get good signal. But that's been so important for progress in AI that we need to address this. And so we've been turning to many things, but one thing in particular has been very interesting recently is using neural radiance fields and variants thereof to basically reconstruct and resimulate what's going on in a real run. So we go out, we drive, we've got multiple cameras around our vehicle, we take that back to the office and train a nerf, and then we can re-render and render that from different viewpoints. And once we can do that, we can do a couple of things. So, of course, we can do evaluation. So here's a little schematic of that. So we can, there's the ego vehicle. And we can basically start, we can throw in a real driving model into this simulated environment and see how it drives. But then we can perturb the starting state and see how robust it is. Does it recover back to a sensible trajectory? And we can do this for many different variations. And so test a lot of out-of-distribution states that are very hard to test on the road. And so here's, that was a schematic. This is an actual running system. So the top's just the visualization from the top view. The bottom's what actually gets passed to the driving model. And we can compare the path that was actually driven by a model with the path that the resimulation drives, and that gives us a really nice metric to keep improving the system. Here's well, the next thing you need to do is then detect when something's gone wrong, right? So you can detect whether you've drifted off the path that you originally took, but you can also detect have you actually collided with something or other things like that. And so this is, the nice thing about having these NERF reconstructions is that you can actually do semantic segmentation in the 3D space, and you get really beautiful, consistent segmentations that then you can use for detecting these collisions. So here's an example where we, force it to keep colliding with things and drive badly, and you're able to again pass in the input and use those segmentations to detect these kind of collisions. But beyond evaluation, there's also a really interesting opportunity for training. Can we train off this synthetic data? And so we've been exploring various avenues, and here's some sort of very preliminary early results around collecting out of distribution states for training, and perhaps put some heuristic that gets you back onto the expert trajectory. And then you can throw those into as augmented data into your training set. And again, very, very preliminary results here, but you can, for targeted interventions, you can actually, massively reduce the number of problems that you see on the real road by taking your real training set and augmenting it with these kind of out of distribution synthetic states. But this area is challenging, right? To really get, and there's a reason that most of the examples I showed you have static scenes. They don't have much dynamic agents, and that's because it's very, very hard to do the whole dynamic scene in this way. First off, you've got to decompose the scene into the static and dynamic agents. You've got to be able to control those dynamic agents. You've got to be able to recompose it and have that look good. You've got to think about traffic lights. They don't move, but they do change their appearance, and that's sort of like not a normal thing, and they change their appearance in a very particular way. You've got deformable objects like pedestrians and cyclists, and of course you've got to get the dynamic behavior to be super realistic. So I think there's lots of interesting avenues for improving this, and lots of potential for solving these challenges. But while we work on that, we're also looking at something called world models that somewhat sidesteps those. So I'm going to switch to this third and final research highlight now. And again, this touches pretty much everything that we talked about earlier. So if you look at this this image here, what's that car doing? Is it pulling out? Is it stopped? And how would that affect our behavior? Well, from a single image, it's very hard to tell. From a short video snippet, it's fairly clear that car is stopped. But of course, it could suddenly start accelerating. And we should be able to anticipate this. As humans, we anticipate what other drivers are going to do. And the different possibilities, even if we're fairly confident of what the most likely outcome is going to be. A world model is basically a generative model that predicts the next state conditioned on your current state and the action that you're going to take. If you have one of these, then, well, you have a fully learned dynamic and reactive simulator. You can do what-if counterfactual experimentation. You can do things like model-based RL and search-based planning in this generative model. World models have been being looked at for a while. The concept is not very new. The term may be a little bit newer. And there's been some great work over the last few years, especially in the world of gaming, and building world models of gaming and then training within that world model to solve the game. And Jan LeCun's also, very, very keen on world models as part of his, path towards an autonomous machine intelligence as well. We've been looking at world models in various shapes and forms for the last few years at Wayve. Our earliest work was dreaming about driving, and here we basically have an auto-regressive model that would predict the next frame on these very, very low resolution video sequences on very simple off-road scenes like this. But using that, we could then learn within that world model to actually drive, and so again, super simple driving task, but it was able to learn to lane follow just within its imagination. More recent work we've been looking at has led to a couple of papers, one called Fiery, one called Mile. And these were definitely helping us improve this future prediction ability. But both of them were fairly highly supervised, either through manual labels or through the use of a simulator. And what we really wanted to be able to do was to leverage that self-supervision thing I talked about earlier, and the large quantities of data we have in our corpus that aren't labeled. And that's what we started looking at. And simultaneously, of course, there's other people working in the field, and this is just a few examples from NVIDIA, DriveGAN, some work from UBC, and the video diffusions work, and a few other examples here, things like Gen 2 from Runway, and another self-driving car called Comma AI that were doing something as well. But we thought we were going to push on this too and see if we could do a little bit better. And 3 or 4 months ago, I guess now, we announced Gaia, generative AI for autonomy. And this is where I come clean and say these videos I showed you earlier on to motivate the complexity of driving in London, these are all synthetic. These are all generated by Gaia. They're not real data at all. And if you look closely, there are definitely artifacts, and once you know that, you can spot it. But in general, this highlights just the incredible diversity of scenes, of weather conditions, of traffic that we're able to basically completely synthetic generate now. So there's a few interesting stories here to tell. One was, we announced this early in June because we were very, very excited about the results we were getting. And so here was, one of the first ones where, we'd see it. It would imagine waiting for the light to go green, going around the corner. It would imagine this whole street, all the parked cars, and not only the layout and the static and dynamic scenes, but also how to drive. Like, it was learning implicitly a policy to drive through this imagination. And you'll see it sort of weaving and navigating these streets. And this got us sort of super excited. And so we sort of went and doubled down on this. And between June and October, we basically did one of these scaling curves experiments. We 10x'd the number of parameters, massively increased the resolution, the number of data, and we threw a ton of GPU compute at this, 100 A100 GPUs for 15 days or so. And, nicely our scaling curve prediction was vindicated by the actual result as well. But the result was that we could go from something that looked like that on the left to something like this on the right. Again, higher resolution, much higher fidelity of traffic and quality, and really a big step up in terms of what we could generate. So here's a few examples of just unprompted generation. Just let it go, let it imagine, initialize randomly, and see what happens. And the amazing thing is that most of the time it just keeps on generating and generating and generating, and it doesn't diverge into some bad part of the state space that it can't recover from. It does happen occasionally, but most of the time it's remarkably stable. It can generate these very, very different conditions, road types. It's trained only on our London data, so it's basically all looks like parts of London, but London itself is very, very diverse. How does it work? Well, super simple. It's basically ChatGPT, next token prediction, like ridiculously simple. So if you want to prompt it with a starting image or some starting text or some starting actions, you can. You encode those to discrete tokens. Those tokens then get passed into this world model. The world model auto-regressively predicts the next token in the sequence. And then once you've got a batch of those tokens, you pass them through a video decoder, and that generates the beautiful video. And you can go and have a look at the paper if you want to read a bunch more of the technical details there. But let's look at some of the capabilities now. So first off, as I motivated at the beginning of this section, the reason for this is that we can predict what might happen in the future and the diverse futures ahead. And here's an example. We prompt it with the same starting point, and you let it then run. And one it decides to go forwards, and the other one it decides to turn right. Here's another one, perhaps more interesting, where again, same starting point, but click play, and on the left, that white car reverses to get out of our way. On the right, the car keeps going forward, and we slow down to let it out. We can also control it, right? This is not just, we don't have to just let it go. We can, but we can also control it. We can steer it. We can change the accelerator and brake. And so in this example, the 4 different panels, they have the same starting point, and we just tell them to do different driving patterns. They're basically sinusoids back and forth. And, it follows those paths, just like, a computer game would, but, with this photorealistic generation. And, if you look closely, I forget which one it is. I think it's the bottom left there. We actually we steer it so far that it goes off the road onto the pavement. Now, that's not something we have in our training data at all. And so it's somehow learned effectively an implicit model of the geometry of the scene. There's no explicit 3D in this. There's no explicit computer vision knowledge encoded in this. It's learned the rules of perspective. It's learned the rules of 3D geometry. Here's another similar example with different conditioning signals. And again, we go off quite off-road there. What's interesting in that bottom left example now is the headlights on the wall, right? So as we get close to the wall, you'll see the headlights lighting up the wall. That would take quite some doing to try to think that through and to code that in. I mean, I guess with a computer game, of course, you could do something like that. But the fact that emerges for free is amazing. And then the other thing that's zooming in on the top right panel is this reactive behavior. So here, we're driving along and we suddenly steer to the right into the oncoming traffic. And we see that vehicle pull over out of the way, which again shows that it's not just some replaying what actually happened. It's actually seeing these objects as discrete objects and knowing how they react to our own behavior and how we react to their behavior for that matter. And we can also language condition it. So, weather conditions rather simply, sunny, foggy, rainy, snowy. And, the snowy is interesting because we only had 1 day of snow last year in London to capture data for, but we're able to generalize sufficiently well from that. Plenty of rainy weather. And then different times of day. So sunlight, twilight, gray sky, night. And again, really sensible generation. And you can do combinations of these things. So accelerate right, we're 15 meters behind a bus, and lo and behold, it creates a bus, and then it allows us to sort of go around and overtake that bus. So many opportunities for taking Gaia forward. We want to, at the moment, we've just shown generation, but we actually want to use this for driving and improve our driving, make it faster, exploring controllability and compositionality further, generating long tail scenarios, and can we combine the best of those NeRFs and world models together. So I will wrap up there. Thank you for listening. Again, I believe autonomous driving is an embodied AI problem, and that those foundations that we've seen over the last few years of modern AI are already accelerating progress in the space of embodied AI. And the research breakthroughs, of which I showed you here, and there's plenty more going on in the community as well, are really accelerating progress and promise step changes in capability. So I will say thank you and just leave this video again for fun.